Hello, everyone. Welcome to MarkTech Post AI live session. My name is Asif. I'm the host for today. And with me today, I have a guest who is Lorenzo. He's a postdoctoral researcher from Switzerland. And he's going to talk about a paper. He's going to explain the paper, make a video, text to video generation without text video data by Meta AI. So I'm going to let Lorenzo explain the paper. I'm going to add him here. All right, Lorenzo, over to you.
Hello, nice to meet you to everyone. I'm Lorenzo, as Asif was saying, and I'm currently at the University of Bern. So today I'm gonna talk about this video, this paper that is very interesting and impressive from a researcher from Meta AI. And you can find here the link of the paper. So if you want to find more details about it, just you can go and read the paper. But we're going to go to see all the details in this presentation before going to see how the model works and to give you an overview of how the model works. I want to show you some of the examples what this model is capable of, starting from make a video with text. So basically, this model gets as input a sentence. You can see here in the left part, for instance, a dog wearing a superhero outfit with a red cape flying through the sky. And the model is outputting this very nice video clip in which the dog indeed is flying into the sky. Or, for instance, you can also write a young couple walking in the heavy rain, and the model is outputting this kind of video. And finally, on the right, you can see also some more sci-fi kind of generation. So hyper-realistic spaceship landing on Mars, and the model is still able to make a nice video. Of course, there are some details that are missing. For instance, you can, if you see the edges, some of the details are not perfect, but this is very impressive for an AI that is generating videos from just text description. So this one thing that the model is capable of, but it's also capable of animating images. So for instance, here, if we input an image of this boat that is sailing, we pass this image to the model, and the model will output a video. And as you can see, now the boat is actually truly sailing. Yeah, as well as before. I mean, there are some details that are not perfect, but still the result is very impressive. And finally, you can also basically make a video from some other videos. So for instance, if you provide an input video of an astronaut, and you can basically generate videos that are similar in terms of semantics as the input video, but are different. And indeed, here we can see that there are two astronauts that are still floating into the space, but they're not exactly the same as the input video. So if you want to look at more examples, check this link. That is the official webpage of the paper. And so there you can see more examples for this. Okay, so what is the design idea behind this model? The design idea was to dissect the video generation from text into two subproblems. Indeed, you try to learn how the world looks like and is described from text image data couples. And then you basically learn how to animate these images by using unsupervised video data. And the main advantages of this approach, so of this make a video, it's that you can basically accelerate training of the video model. Indeed, you don't need to learn very multimodal representations that are present in video data, but you can just try to generate an image given a text prompt and then trying to animate this image. And as I was mentioning, it's very important that this approach does not require text to video data, which is very hard to collect and very hard to label. And finally, this model is leveraging the current image generation models, which are very powerful. And indeed, as we have seen in the previous examples, is able to generate high quality videos. And the main difference, I mean, right now there are a lot of text to image generation approaches that are actually becoming very popular, like DALL-E, and there are many others. And they're able to generate very nice images from just text. But for the text to video generation, it's much harder because, as I was mentioning, there aren't many text to video datasets available. And of course, since videos are much more high dimensional than images, just a sequence of images, this is much harder for the model to learn meaningful representations. And of course, there has been some approaches in the past to tackle this text to video generation problem. Here, I'm just mentioning a couple of them. And for instance, this COP video is another very late approach to which the make to video is going to be compared. So we're going to see results of this make a video paper and the results of COG video as well. That, if I remember correctly, is just trained with fine tuning on the video text data. So it has to basically train on text video data differently from make a video. So this is the model overview. This picture is taken directly from the paper. And the model is composed of three main components. The first component is the text to image model that is going to get the input text and provide an image. Then, of course, we need to animate the image. And so we need a spatio-temporal decoder. And so this image is going to be extended over the time dimension. And finally, if we want to have a video with more frames, then we need some sort of frame interpolation. So now I'm going to describe the three components that the authors are using. So first, the text to image model. And they said that basically they use the core components of the model of Raresh et al. From 2022. That is this article that is titled Hierarchical Text Conditional Image Generation with Clip Latents. That is also called Unclip or DALL-E 2. And so this is a text to image model. So if you write a sentence and provide this sentence to the model is going to output your image. And as you can see, the results are very, very good. You can, for instance, a teddy bear on a skateboard in Times Square, and you get this very nice, realistic image. And these kind of models, this model, to be precise, but in general, these kind of models work in the following way. So since you have an input sentence and an input image, you're training your model on these couples, and you're using this CLIP objective. That is, a CLIP stands for Contrastive Language Image Pre-Training. Basically, this is a way to push close into the latent space images and text, so that an image and a text of possible couples are close to each other, while text and images that are not related are far from each other. And then once that you have described and built this sort of embedding, after having trained on many text image couples, then you basically try to predict and generate images from this latent space. So once that you have your encoded text here in the bottom left, then you pass this into a diffusion model that is a generative network. And then, as you can see, you can still generate an image that is connected to this Akorji playing a flame-throwing trumpet that is different, though, with respect to the one that I've seen into the training phase. And so in the make a video approach, they use this text-to-image model. Here I am highlighting the parts of the model overview that belong to the text-to-image model. So you have this prior net P, they call it P, that generates the image embedding. So given the text, you generate this prior embedding. And then you have your decoder that we've just seen. So this diffusion model that is generating a 64 by 64 frame. I'm highlighting it here. And there are also two super resolution networks that will upscale your image from 64 to 64 to higher resolution if you want a higher resolution for your final video. So to 256 times 256 and 700 pixels more or less. Then, of course, this is the second component of the model overview. So since we need to animate the image that has been created with the text-to-image model, we need a spatio-temporal decoder. The spatio-temporal decoder is going to generate 16 64 by 64 frames. And so at the beginning, basically, we are randomly sample our generator, and we're going to obtain a sequence of frames. Of course, at the initialization, this sequence is not temporally coherent. So for instance, if we are inputting a person doing yoga outdoor during a sunrise, if I sample for 16 times our generator, I will get 16 different frames of a person performing yoga. But then, of course, I need to have our video to be temporally coherent. And so I need some other processing like pseudo 3D convolutional attention layers to make the video coherent. And so this is another part of the model. And then another spatio-temporal network that is needed to increase the number of frames into the video clip. So I'm not going into the details of the spatio-temporal layers that are part of this decoder architecture, this, spatio-temporal decoder, to be precise. But the authors propose this pseudo 3D convolution and spatio-temporal attention that are some tricks basically to perform, to be more efficient in terms of computations. Indeed, the 3D convolution operation is very, very computationally heavy, while if you use this pseudo 3D, so basically a 2D plus a 1D convolution, you can gain a lot in terms of computational performance. And similarly for the spatio-temporal attentions. And then I was mentioning before, we need some sort of frame interpolation, because if we want a video of many frames, 16 frames will not be enough. We want a longer video. So we need this network that is basically increasing the number of frames by interpolating. And they do this by masking some of the frames. And this will help the model to learn how the video is basically flowing and to increase the numbers of frames. So to train the full model, you need basically these three components that we have just seen. So the text-to-image model, the spatio-temporal decoder, and the frame interpolation network. So these three components, as the authors stated in their paper, are trained independently. And the text-to-image model is first trained. Then there is this decoder and super resolution on just images. And only finally, you are basically trying to fine-tune your model on videos, unlabeled videos, so such that your frame interpolation network is basically able to create a video from a single image, but without needing the labels and the labels for the videos, which are very hard to obtain. Okay, so some results. Here, the authors basically have compared their make a video versus state-of-the-art approaches on the UCF 101 dataset. That is a very famous dataset for action video recognition. But here they're just comparing in terms of the quality of generated videos. And as you can see, their make a video approach is much better than the precedent approaches in terms of freshet video distance. And they also perform some other evaluations, in this case, human evaluation. So they asked some people to evaluate the quality of the videos that were performed, that were generated by make a video and by other approaches. And also you can see that the quality here of the make a video, according to this human evaluation, are better than the comparisons. And yeah, here another couple of qualitative results. So this is a direct comparison between make a video, that is the bottom row, VDM and cog video, two of the approaches that I mentioned at the beginning as in the related words. And as you can see here, the text prompt that was input to the model was busy freeway at night. And you can see that, I mean, the first two models are able, I mean, understood the semantics and are able to generate meaningful videos. This is, of course, the sequence of frames into a video. But the cog video, of course, is much better than the other ones. You can see there are cards and so on and so forth. And with this, I conclude this presentation. Here I'm reporting again the paper link if you want to read the paper, and there is also the paper website if you want to see more examples of make a video. And of course, if there are any questions, I'm available to answer them.
Thank you so much, Lorenzo. It was such a nice presentation. I hope our viewers have enjoyed it. Folks, if you have any questions or if you want to reach out to us, you can contact me at this email address. Also, if you want us to cover any specific papers in the future, you can still email us on this email address. If any of you who is a PhD scholar, postdoc scholar, or a research company in AI, they wanted to give a presentation or explain certain concepts or their product, feel free to reach out as well on this email address. So with this, today's session is over, and I wish you guys a wonderful day, and we'll see you in the next session. Thank you, Lorenzo.
Thank you.